talk a bit about polars today. My pet project for almost 3 lockdowns now. And last talk was a bit bottom up and really close to the middle. And today I'm going to talk a bit about polars in an overview. Going to talk about what polars is in a nutshell. How we can claim the title of this talk, blazingly fast data frames, and how you're gonna use polars coming from a pandas background, and then we're gonna go through polars expressions, and that will be a lot of code examples and code snippets to see how it works. Yeah, so. In a nutshell, polars is an in-memory query engine, DataFrame library that's written from scratch in Rust. Rust is a memory-safe programming language with performances similar or even better than C or C++. And with memory-safe, we mean that Rust has a new concept which makes sure that you cannot have null pointer exceptions, cannot access memory that's not yours. Only if you use safe Rust. So Rust has got 2 programming languages. You could say it's got a safe programming language and an unsafe programming language, but most of the language is safe. And this gives a stronger guarantee that you don't have seg faults. That's actually you don't have memory-related bugs. But it does give us full control over memory and close to the metal. CPUs are getting, well, if you want to write an optimal performing computing language, you want to have full control over the memory. CPU is really fast, but memory access is often really slow. There are a lot of latencies we want to hide. We can do this in with a lot of tricks, but we want to be able to do those tricks, and that's why we need a language that gives us full control, which Rust gives us. The second thing where polars is written on is the Apache Arrow memory model. The Apache Arrow project is initiated by the founder of the author of Pandas. He noticed that a lot of compute, a lot of serialization was wasted. A lot of compute was wasted in serializing from data over the wire to another process or to another tool. Let's say I use Spark, and in a Spark node, I also want to go from Spark to DataFrame, to a Pandas DataFrame. Then the data was first serialized via Pickle and then deserialized via Pickle to Spark, or the other way around. And this is very wasteful because the serialization method, be it Pickle, be it JSON, be it another binary serialization method, is often not meant for columnar or big data. Aero aims to improve that, and it's succeeding at that. It's becoming the standard of memory columnar memory storage, where you store data in a columnar fashion, and it's getting the standard of big data or data communication. So you can send Aero over the wire to another process, and with a lot less deserialization cost. In processes, so for instance, in polars, we use Aero. In PyArrow, we also use Aero memory, which means we can just swap pointers. This means that we can send gigabytes within the same process free. It doesn't cost anything. We just read the same data. This is not possible for pandas. If I want to use pandas memory, I cannot always access that, and vice versa. Pandas cannot access Aero memory. So for instance, pandas uses PyArrow to load Parquet data. PyArrow parses this Parquet data, loads it into Aero memory, but then it still needs to copy from Aero memory to pandas memory. So you have a double copy, which is wasteful. So yeah, Aero all tools that will be based around Aero will essentially be able to read each other's memory for free in the same process. And on distributed compute, we can use the Aero flights. It's called the Aero way of sending data with less serialization overhead. So Aero is becoming the future of one, columnar storage, and two, data flight, data sent, data over the wire. And it's already becoming big, but it will be becoming bigger and bigger over the next decade. So what this means is that any tool will have an Aero, support. I mean, this means, yeah, this is great. So we bet on a horse that's winning in the future, right? Yeah, Polars is really written for the hardware. This is more down to level, but the free launch is over. CPUs are not getting faster anymore. We only get more cores. But if you have more cores, you need to write parallel programs, which are totally different than sequential programs. So you need to adapt your programs to benefit the growing amount of transistors on the chip, because we're not getting faster, but we're just getting more cores, right? And in the old days, we just had to wait 2 years, and yeah, we just get a speed bump for free. So there was a free launch. And the CPUs are still really fast, are really fast, but accessing memory is super slow. So we need to do a lot of tricks to hide these memory latencies. But I don't want to talk about this. Yeah, the title claim. So if you take these two great technologies, being the Rust programming language and Aero, with a lot of time during 2 lockdowns or 3 lockdowns, I don't know. Yeah, too many. We can have a really fast query engine. And in fact, Polars is one of the best performing query engines out there. I think we're all Pythonistas here, but we always were really bad in performing. So Pandas is down here. Here is R with data table, which is a really fast DataFrame library. Spark in memory, ClickHouse. This is a columnar database. Julia. These are the results of Polars on every data set, the largest data set it finishes. So these are the easy questions in group by. These are the joins. So the joins are twice as fast as, oh no, what's this? 5 gigabytes. This is also the group by, but the advanced questions. And these are the basic questions for the, no, okay, these are the easy questions, basic questions for a group by operation. These are the advanced questions for group by operations. I don't know the order, forget it. But it performs really well. That's the, yeah, that's the idea. Yeah, so here's the data. So here you see go look at this benchmark itself. This is called the database benchmark. They've done a benchmark on the group by operation and the join operation, which are one of the most expensive operations you use in a query language often. And they have really easy questions. So the easy questions are just group by ID1 and some version 1, some V1. But the advanced questions are more complicated, where we group by several columns, or we do a Pearson correlation between 2 columns in the group by aggregation, or we compute the 2 a sorting index. So we group by A and then we sort by B and take the largest 2. So those are more the advanced questions. And it turns out that Polars, especially at the advanced questions, because Polars has a concept of Well, there's this concept of a query engine with an expression language, which is with this expression language you can actually combine anything or a lot without the need of custom lambdas, without the need of Python lambdas, which makes it really expressive, but also keeps it fast. But we will get to this later. Yeah, so the gist of this is that we get a really fast, arguably one of the fastest query engines out there. So that's cool. So let's see how this how this feels in real life. So let's start with pandas. So what I don't know if you know this feeling. What I often did not like about pandas. So here you can see my threads. So I've got a machine with 12 cores. You see them? No? Yeah, but that's because they're not used at the moment. So now we're gonna run the pandas group by benchmark on the half a gigabyte data set. So now it starts, and now you will see one thread being used. Here it is, and it toggles between threads, right? Because one thread gets warm, and then we go to the other one. Here pandas is busy, and we constantly see one thread at 100%. But we have 12, so this feels, yeah. The other threads are like, how are you doing? Need some help? But no, I'm fine. Yeah, all the time we need to wait. I often did not like this view of one thread being ran all the time. So it's still busy and still, yeah, mostly one thread, and it's toggling between threads. It's a bit too small, isn't it? Well, it's still going. It should take, I think, 50 seconds, 60 seconds. Any questions? There we are, 64 seconds. It's a bit slower because we were doing a lot of, I think we're having a lot of programs open. So now we do the same in Polars, and look at those threads. And also you see all the threads are utilized, and we're already done, 8 seconds. So 64 seconds versus 8 seconds. So yeah, you can see this truly makes a difference. And we were able to utilize, I don't know if it was visible, we can run it again, but we were able to utilize all the threads, and mostly we can, it's not always the case, but sometimes you have embarrassingly parallel algorithms, that it's very easy to distribute all the work on all the threads. But it's also often the case that it's not the case. But this is sort of a real-world benchmark, and you can see we can utilize most of the threads. So that's great. So yeah, that's one thing. One argument of using Polars. We have performance. We have the best performance there is, or among the best performance there is. So the performance in the database benchmarks is 5 to 20 times pandas on a larger data set. So pandas does worse when the data set gets larger. And we also have better memory requirements. So you have a sort of RAM needed to load the data set, and you also need some extra RAM, right, to be able to run your algorithms. If you have a join, you need to create a hash table. If you do goodbye, you need to create a hash table. You also need room for these data structures you need as intermediate structures. According to the pandas development team, they need around 10 times data set size. And they say to themselves, pandas is a memory hog. Especially if you grow bigger than 5 gigabytes, it needs a lot of memory to be able to finish the queries. Polars needs about 2 to 3 times the memory size. So in both performance and in memory usage, it's a big win. Then there are also some some things which are good, but more from a design perspective. And one thing is, because everything is written from the ground up, we've got first-class data types, right? Which means that missing data, we can encode missing data as being missing data and not using the NumPy or the floating point number, not a number for missing data. So in pandas, if you have integers in a column and you'll get one, or you add a num, or you will get a num because of a join which leads to missing data, or goodbye which leads to missing data. This whole column will be coerced from integer to a floating point number, which is not ideal, to say the least. Yeah. So your data types just are changing underneath of you, and also they are not consistent. So not consistent so you can do for instance, it's okay for data type to be cast when you do multiplication, right? If you multiply an integer column with a floating point column, it's okay to coerce to a floating point, right? Because that's more. But it's not okay if one time it stays the same, it stays integer, and the other time, because the other column has missing data, it becomes a float, because then it's data dependent. And you want your schema to be independent of your data. Does that make sense? Yeah. Another one is string data. In pandas are boxed Python objects. This is a really terrible one. So boxed objects means this is how the data looks. So if a pandas column with strings, right? So if 3 strings, and those strings, they are boxed, which means you get a pointer, and this pointer points to a totally different place in memory. And your CPU gets data via caches. And if your data access is predictable, you're really fast. If your data access is unpredictable, which this is, because every pointer goes to another direction, I think it's like 300 times slower. It's insanely slow. You also waste a lot of memory, because now in the blue I have diagrammed it as fitting around the memory exactly. This is not the case. You will use more memory than you need for your string. And there are also places in memory, intermediate places, which you cannot use. So you get fragmentation, right? So you will have a lot of fragmented blocks of lost memory. So it's bad for 2 things. Memory fragmentation, so you waste a lot of memory, which you could use for nicely concatenated tight memory, and it's super slow. Yeah.
Given the strings are immutable in Python, why did they get this?
Given that strings are
immutable, so like why did they go for a boxed implementation?
I don't think strings are immutable.
In Python, strings are immutable.
They are mutable. Yeah. But they had to go for Python objects because
strings tuples are immutable in Python. So they could have gone for a numbers implementation.
Tuples are different from regular, right?
No, strings are also immutable.
What happens when you mute
new object creation? I mean, when you have something and stuff.
But they're still boxed, so the box doesn't say anything about mutable access.
I mean, if it's not mutable, why would you allocate a random memory location rather than collocating everything and trans? For example, assuming that like this string array, each ultimate string array will be immutable, right? You can't have them next to each other in the memory, because you know that if something is going to change, it will allocate new memory. There has to be a reason for why they do that.
Yeah, because they use NumPy, and NumPy doesn't have a string. NumPy wasn't made for a DataFrame library. So NumPy So they use NumPy arrays.
Okay.
NumPy just has floating numbers, and Python has strings. So we can just put the Python pointers into the NumPy array. That's what you can do.
Yeah.
That's what they do. And about the mutableness of strings, I don't.
I have verified just like Python string immutable and says
Immutable. Oh,
one of the immutable.
I don't know about that. Could be. Yeah. Okay.
It's designed for mutable effects. Then they extend strings and they use design effects.
Sorry?
Because they use NumPy.
Yeah.
Designed for like more mutable types.
Yeah, they use NumPy because it was available and it saves a lot of work.
Yeah.
But NumPy was not designed to be a query engine. That's the thing. So.
Can I get a response question? Does NumPy make the support Aero?
NumPy does not support Aero. Pandas has Aero integration.
By testing NumPy then?
No. Pandas still uses NumPy, but it uses Aero for parquet parsing. Yeah. So they use Aero for the serialization part. Yeah. But I'm not a Pandas expert, so
if you are not, I don't know who it's. Yeah, written the whole thing.
So another thing. No, here I also say I never understood too much. I'm not a Pandas expert, so I was more often the NumPy guy, but I work with colleagues who use Pandas, and then I read Pandas code, and I'm always like, what are we doing? Reset index, set index, indexes. I never understood them much. Multi-level indexing. If you think about what they do, I think they implemented it or as a hash table or as a binary tree or something. They need to compute that thing when you reset an index, which takes work. I think that the usage of indexes in the wild costs more compute than that they save. That's my assumption. I don't know if this is true, but I think indexing has made the code more complicated. And code is read more often than written, right? We read code a lot more, and we want to understand what happens. So I designed polars to be like SQL. SQL is declarative. You say you want what you want. You describe what you want to have and not how to do it. So if I want to have a sum of a column, I say so, and I don't say I reset my indexes so I can get the sum. So if you don't have indexing, you can remove ilog, you can remove log, because accessing now has become predictable. You can just do it the same as in NumPy. So the first axis is row axis, the second axis is column axis. And if you have to use the first axis for numerics and the second axis for strings, then the first is for the rows and the second is for the columns, also predictable. And we have expressions, but we will get to that later. And if you do only strings, then it must be columns because there are no row strings, right? So this means we can just, it's almost the same, but it's more similar to NumPy. Because we don't have indexes, there's no ambiguity, and we have predictable indexing. So yeah, that's a sidetrack.
But you're not a drop-in replacement for Pandas. You have to rewrite your code.
Yes, Polars is not a drop-in replacement for Pandas, not at all. So I have taken the liberty to write my own API and do things better. Yeah.
That would work adoption.
Yeah. So be it. Yeah, no, it's not a drop-in replacement. There are a lot of drop-in replacements for Pandas who claim, drop in. And yeah, I think it would be a pain in the ass if you do that. And I think it's also good to learn from the past. So this is another thing. In Pandas, there's a lot of copying around. because we do things ourselves, we want to often write pure functions. Pure functions means we don't want to mutate this data frame, which we assign df2, but it points to df1 as well. And then we mutate df2, and then df1 is also changed. This is often not what we want, and it's hard to debug. So we make a copy. But a copy means we clone all the data to another memory. So doubling the memory, being slow. So yeah, this is how a copy in pandas looks. In polars, we have a reference counter memory. So this is the memory, and we wrapped it in a reference counter. Python objects are also reference counted. So reference count means you just count how many references, how many owners are referencing this memory, and if this counter is 0, we delete it, right? There's only one gotcha. By having something reference counted, it is immutable. It has to be immutable, or you have to put it in a mutex, so you can access it only with a single thread. We've chosen it to be immutable, so we cannot modify, we cannot mutate Polar's memory, but we can copy, and the copy is just a pointer. So copies are free, right? They're essentially free. So you get copy on write semantics. You don't have hard to debug. Changing this data frame will change that data frame. So it's easy to write pure functions, and you don't have your logs anymore with this transfer thing. Do you know this?
Yeah, every day.
Every day, right? Setting with copy warning. That's.
Does this also mean that you don't have any methods assigned to your data frame object or whatever, and everything's a pure functional, or can you do still stuff like df dot long df dot this df dot that? Yeah,
you can still do. You can. There is an eager API which is not a drop-in, but which is very similar. But idiomatic polars is different. So yeah. So we have an eager API, we have a semi-lazy API, and we have a lazy API. And idiomatic polars is semi-lazy and lazy. And I call semi-lazy because semi-lazy has all the good things from eager. In eager, we like to hack in a notebook and see directly what happens. And we don't want to write, collect, and right. We want to explore a bit, play with the data. And semi-lazy is a bit of that. But yeah, by semi-lazy, we still have lazy expressions, and this provides me as a query engine designer with context. I've got context of what you want to do. You use this expression in a group by, which means you want to do something different than when you use this in a select statement. And this context I can use. I can optimize for you. I can shuffle things around because I didn't execute it directly. I see the whole intent of the query. I see the whole intent of your expression, and hey, maybe we can do things differently and do it faster. So yeah, let's make. I think this is a bit abstract, so let's make this a bit more clear. So I'm going to go through just some examples. We're going to start with a simple data frame. It's got a column A, which are some integers, a column fruits, which is a string, a column B, also an integer, a column cars, also a string, and a column optional, which has got a null data type. So the null data type doesn't change the integer, we just have a missing data concept. I'm going to explain about expressions, and expressions are operations which you can chain. And an expression has a sort of a contract, and the contract is that an expression works on a column and it returns a column. So it works on a series and returns a series. And what this series means changes per context. And we're going to start with the easy context, which is the select context. And there, this series always means a column, right? So I can select the column A, I can select the column B, and here B also is an expression, but we invert the column part. So the B is actually a string. And this can be ambiguous because it can mean that you also want to say, I want the string B. So if you want the string B, you have to use a literal expression. And a literal means just the literal value of a string, right? And we have a column fruit. So we can select this and voila. And it's really easy to, we select a new data frame. This is simple, right? Sort of. We can also use, it can often be the case that you don't know the exact schema of your data frame. You don't, especially in lazy, you do stuff and the schema changes. So with schema, I mean the column names, the D types. So you can also select columns with a regex. So if you start the regex with this character, and you end it with this, which means start of regex and end of regex, then you can select regex columns by regex, and now we select A or B, and we do a sum. So this is quite expressive. We just say, hey, select me this, and do a sum, and then we get those. I should mention, it's also this easy to write parallel programs. Every column is executed in parallel. So you could, for instance, do this on a data frame with 1,000 columns, and you will see all your threads being used. So parallelism wasn't ever as easy as this, I think. And we can also select the columns with a list of column names. So that's how we start an expression. We can also select all the columns. Then we just say all, and we get all the columns. But let's say I also want to select all the columns in reverse. Then I can just select all the columns, say reverse. But then we have a naming, we call it collision. So we give every new column a suffix named. So suffix means after the name, put this string and reverse it. Voila. Also very easy. And there are a lot of expressions. So you can see how you can, what you can do in pandas in a pipe, you can put in pointers in a single select statement. And if you want the sum for this column, and it's sort of a super describe, right? In the describe, you get this stuff you want to see, and here you can define the stuff you want to see. You can also sum stuff, and if one of your expressions returns a single value, for instance, a sum would return a single value, then this single value is broadcasted to the whole shape of the data frame. So, for instance, the a sum would produce a 15, and because the data frame height is larger, we broadcast this, right? Then there are also the expressions also have specialized namespaces. I think they are familiar. We have the .string and .datetime namespaces with specialized functions. For instance, here we use a string.contains and then select everything that every fruit which starts with a B. But this actually is not a select. What this does is it creates a Boolean array, a Boolean column. Clear, right? If we want to use this filter, we can pass this predicate to a filter. And in pandas eager, we are more inclined to use the quotations. So I think we would make a mask and do things here. I think in idiomatic polars, I prefer using English language names like filter, like select. Like it's very easy to read and to not mismatch. For instance, if in the quotation mark, if you put a mask and the mask is defined by a variable, and the variable is just named A, then it's already, okay, what's in A? Do we select rows or do we use a predicate? So it's dependent on the data type, what goes in there, right? Does this make sense? So for instance, in pandas, we could also do this in Poland, but we could say a mask and columns, right? And then columns could be, the mask could be some booleans. And column could be some string columns, right? But I think we can do the same if we put in, then we get a different result. So if we have badly named parameters, we get a different result from the same use cases of the indexing. So the index is dependent of the data type of the arguments you give it. And I think this can be done correctly, but it's also hard to misuse. And by using a filter, you must pass a Boolean predicate. So it would give an error if you didn't do that. So it's harder to misuse such kinds of things.
Is there a difference between predicates and select predicates? I think 2 cells above this one.
The question is there a difference between predicate and select predicate? How do you mean?
Does it return the same value if you just print predicate instead of do select with it?
Yeah, so that's the context. So this is an expression, this part, and an expression does nothing without a context. So the context depends the result of this predicate, of this expression. So if you print expression, we just see we get an expression object. It's lazy, it doesn't do anything. And this will yield a different result in a group by than in a select, for instance. So you can make these predicates or these expressions also outside of the context, outside of a select, in a list comprehension, for instance, and pass them later, right? Filters, we can do it on the data frame itself, but we also can do this on the expression itself. This means we can combine filters on different columns. And if we, for instance, do sums, we can sum a single. So let's say we take A. So now we select A, where the column fruits starts with a B, right? So let's also select fruits. Then it's a bit more clear. Ah, yes, I do a filter. Yeah, good one. Yeah, and so now we select fruits based on the predicate, right? And we can sum this thing. But we also could select another column based on some other predicate from another column. And we could also sum that. So we can, yes? Yeah, so well, if the length is mismatched, you get an error, because that's also what you want, because that's you get an error if you do something that doesn't make sense anymore. But you can use this to get you can, for instance, you can also use this in a binary expression and use this with column B. So
but wouldn't it be better if you would build those reason codes?
In?
The length doesn't.
No, I've been thinking about that, but then you get so you have a column, and those rows have a semantic value. So if you fill those with missings, then they shift, and this value is not correct anymore. So you want an error in that case. I think that's also why you were sort of.
It's a bit unclear what this discussion is.
Sorry?
It's kind of like a concatenation of two different data frames or columns, right? What you do here.
Yeah, you can. So you start with a base data frame, and you can take this base and derive any new thing you want from it. That's sort of the. So it's not a select in the pure sense. No, you do more than a select. Yeah, okay, but semantically, it's more than a select. But I think you can also do this in SQL. I don't know if you can do the filtering in SQL. Yeah, subqueries. So semantically, it's a derivative of the select.
Select of steroids.
Yeah, it's a select of steroids. Especially if you, yeah, that's how you can see it. So you can do the filtering, but I think you must agree that it's powerful that you can do filters on different, you can combine those, and it's also parallel, and we can just do a lot at once. And we can also, as you can see, we can also do binary expressions. So we can do compute, and we can, all these complex expressions, we can also write functions to create those. Or, for instance, have a function which means take compute rank, for instance, which is consisted of those expressions, right? And then this function does it. Then we have a compute rank function, which produces an expression that computes the rank, right? So you can create readable, readable things from this.
Would it maybe make more sense to name this something else, since it's a little bit different from the usual solution?
Oh yeah.
Name it DataFrame concatenate or something, so that.
I wouldn't. You can rename the columns.
I don't mean the individual columns, but the command. So not df.select, but something different to indicate that it's a slightly different operation.
Yeah.
Well, in SQL, it's still select.
Yeah, I prefer the select one.
Ritchie?
Sorry?
So I'm having a bit of trouble of reading what you're trying to do here. So the select is giving you the first column.
Yeah.
Which you filtered, which is A. And it's only returning that column, and then you have also a filter on B, and you're doing something extra there. I was kind of expecting this to return at most the 3 columns you started with.
Can you be quiet here? I want to understand the question. Okay, come again.
So if you scroll up a little bit to your data frame.
Sorry? You want to see the data frame?
If you scroll up a little bit, because you have a very small data frame, right?
Yeah.
So when you did the select statement, the first time I was kind of expecting it just to return all fruits with a B in it. Or not, that don't have a B in it. So when you just had the first entry, so call a filter, call fruit string contains not B.
So do I need to scroll up somewhere here?
No, at your select statement.
Yeah. Let me see, where were we? Here?
Yeah, exactly. So when you ran this without the sum compute column.
So without the sum compute.
Yeah,
like
this. Yeah. Well, it's this pretty much. So now you get 3 results.
Yeah.
And then you're also going to filter on B. But that was the wrong interpretation because you're going to concatenate the second item, right?
No, you're not going to concatenate. So those are different columns. So the first column produces this. So let me, and the second one produces this. And you see because the filter from the first column is on fruits, and the filter on the second column is on cars, we produce different lengths.
Yeah.
And that's not allowed in a data frame. So data frame, the column should have the same length. So if you run this, you will get an error. And you can solve that by doing an aggregation. That is allowed. So what we're doing now is something we make up. I don't know if this makes any sense, but it could easily make.
Some of the other one.
Sorry?
You had the sum on the other one, the first one.
Oh yeah, right.
First entry.
Sorry. Oh, this one. Voila. Yeah. So it's more to show the expressiveness of these expressions, that you can do things you normally wouldn't do in a select. So that's also the discussion we started a bit. Okay, does this make sense? And then the question was, if those columns if those filters return different length of columns, do we want to fill them with nonce? And I would argue that you don't want this, because the rows mean something. So the banana means something with B being 4. And if you shift this, you want this intent, you want to have programmed this intent, but not that this has happened automatically. Then you will get very hard to debug bugs. But yeah, so does that answer your question, sort of?
Sort of. I think it would be really explanatory if you could write a SQL query of this. I don't expect you to do that now, but it would be helpful.
Yeah, you can just write a SQL query with this. So you can do the filter on the DataFrame level as well. So you don't have to do the filter in the columns. This is more SQL++. It's not. This is something you can do in polars, but this is not per se something you would do in SQL.
No, but if you would produce this with a SQL statement and a union all, for instance.
Sorry?
If you could produce this with a SQL statement with a union all, or something like it, then it would just be really explanatory if you put that in a comment. Because I still don't know exactly what we're doing. I just know it's cool.
Ah, right. Yeah, we're just combining predicates, or combining. I don't know the SQL statement for this, so don't ask me to.
Not right now, at least.
Okay. So this is already what I said. You can do arithmetic on those expressions, and you will get an expression tree with these can get pretty complex. And we also do some simple expression simplifications. This is a very easy one, but there are a lot of things. For instance, you can have some variable being equal to 1, and you haven't said it like this, but it after calling some other func, it has become 1, right? We can imagine this to happen. Let's say we have a billion, I don't know, a lot of rows. It would be wasteful to multiply this whole expression times 1. You need to compute that. So we have some optimizations which remove simple expressions which we can prove are the same. So true, the literal true, or a predicate column is always true. So we don't have to do this operation. And this can save a lot of time. And this would not happen if you write it out by hand. But if some function evaluates to this, which can happen, yeah, you don't do this wasteful compute. So that's great. Yeah. Let me see, what did we want to? Oh yeah, this is, so the expression we've done till this far, we're all on one column, right? So we can do stuff in one column. We can filter, we can reverse, we can interpolate, we can, I don't know, we can sum, we can aggregate. But often you also want to mutate something. You want to combine stuff. You want to, if this is true, I want this to be that. If that's true, if it's false, I want it to be this. In polars, we do this with a when, then, otherwise expression. So we have a predicate. So when takes a predicate, or a mask, if you think more in NumPy, something that evaluates to a Boolean expression, to a Boolean column. So when fruits equals banana, then I want column B, the values from column B. And if it's not, I want the value -1. So if we run this, we see that banana, let's also show B for completeness. So if it's banana, we see that And let's rename this thing. Bar. So if fruits is banana, we see that B is 5, but bar also is 5. 4, 4. And if it's an apple, it's -1, which we wanted. Yeah?
Were they the same column name?
Yeah, that's something that will be an error later. They were the same column name. You mean this, right?
I was wondering what would happen.
This will become an error in the future. This is still something that this will not be allowed. So it's work in progress.
We choose for not allowed, or we just call the second one B2?
Sorry, I have a question here. Can be a bit, yeah?
If the one choice you can make is this is not allowed, you could also choose to just automatically call the second one B2 or B underscore or something.
Yeah, yeah. Still thinking about what to do here, because I want my schema to be, so I have a full lazy mode and I want the schema to be predictable. I want to know what the schema is. And I think we can do this. Yeah, we can do this. I still have to, yeah, maybe we add a name or maybe we let the user define it. Because you can pretty easily add a suffix or something, or it's still undecided. We'll get to that. Okay.
If I understood correctly, you can alias it, whatever. Oh, never mind. You're just doing that.
Sorry?
When then otherwise can just end with an alias, right?
When then otherwise, and then?
You can put an alias on that.
Yeah, you can put an alias in that, indeed. Like that. And then you can also do columnar. You can also do, so this is a simple one, but you can also do complex horizontal aggregations with a fold expression. Does anybody has some functional programming experience? So a fold, shall I explain it? Yeah. A Haskell fold. A fold is a recursive function that's executed over in a list. So if you, yeah. Sorry? Yeah, a fold is a reduce. It's the same. So a fold has two arguments. It has an accumulator, which you initiate with a value which makes sense for your aggregation, and then it has a binary function. And in this case, the binary function is a plus. So a plus has two sides, right? It has the A and B, and you combine it into one. And then you take the first value from the list, and that result is assigned to accumulator. And then you take the second value from the list, and that result is assigned to the accumulator. And so you recursively do that until you have depleted your list. You can also do this in columns, right? So Polars has a horizontal sum. You don't have to write this manually. But if you have a complex aggregation, which is not a mean or a sum, or you can write this yourself. And even though we use a lambda here, the lambda only does the dispatching to columns, so it will be fast, right? Because we work on the whole columns. So we select A, we select B, and then we do the fold, and we take the function A plus B, and the accumulator is null, 0, because if 0 is the correct state for a sum, the unity. I think it's called the unity value for a sum. And then we select these are also expressions. And the types are inferred, so you should read this as being column A, column B, and then we take column B squared and column A divided by 2.0, right? Just to show we can combine these things. You can make a list comprehension and do complex stuff, and then we run this, and we have horizontally squashed these functions in. Well, actually, this is already quite complex because it's not a horizontal sum anymore. It's a more complex because we take a column squared and we take a column divided by 2. So just to show how expressive these expressions are and how you can do things you intend to do without relying on the library writers to prevent you with a keyword that does this, right? And we can also do this with strings. We have a concat string function, and you can also do it with a fold. Please don't do this with a fold. Its algorithmic complexity is squared. I will explain later why this is the case. This is to do with memory. So that's why we have a concat string function.
You have no more indexing, so you've lost lead and lag, right?
I've lost what?
Lead and lag. You cannot support these, can you?
What do you mean with lead?
Lead and lag, so taking vertically, say you take column A, but you take a value from one row below. That would make no sense anymore, right?
In this specific query, or just at all?
In general.
Oh, we can do this. You can do a, for instance, A and a shift. This?
Yep.
Yeah, if you want this, sure.
But you need to have it properly sorted some way for this, right?
Yeah, right. You have to. That's right. So if you want an index, you need to add one. So you can say height, right? Like this. And then you have an index. So if you want one, you can create one.
That makes sense. Yep.
Yeah. So yeah. Okay, now we get, this was the select context. Was that any questions? Then we go one deeper. I see I started directly with all the, so let's start with the aggregation, but a bit less exotic. So we can, again, we can just combine this stuff how we want. So we can do a sum, right? I think we know this in pandas with their strings. We need to write strings. Oh, how you combine those strings? I don't know. That's so we can also do this. This is synthetic sugar. So we also have pl.sum, which is actually synthetic sugar for column b.sum. Just what you want. You can combine with a fruit. So these three aggregations I did are really aggregations, right? So you take the groups and you aggregate them to one single result. You can also have, this is also an aggregation. This is clear, right? Something that's not an aggregation is something like a shift operation, a lead or a lag. In Polish, it's called a shift. If you do this, you don't produce a single value, but you shift the values in the group. So what you get returned is a list of the groups. Does that make sense?
No, what's happening with shift?
So shift takes, so this is, let's print the data frame. So shift takes the group, in this case banana. So we take B from banana, so that's 5, 4, and 1, and then we shift it by 1. So we will see we get 5, 4, and 1 is shifted off, right? And the first value is replaced with a null because we dropped it. That's what the shift does. We can also do a shift and fill, for instance. Here we fill it, and then we sum it. So you can only, then you only sum the lag. We can also do a filter here and then sum that. So we can, again, combine all those predicates with the business logic we need, or we can reverse by the groups. But it can also be the case that you want those lists, that you want them flattened, right? So that you want the lists in the order of the groups on the data frame. Does that make sense? So let's say I take this data frame and we have cars, and then we explode by cars. So cars is a list now, but we want to have this exploded, and then it stretches out this list again, so it fits with the groups you add. Be sure that if you do this kind of stuff, that you first sort by the group, by the column which you want grouped. In this case, it's cars. Is everybody following me, or am I going too fast? So this is, I think in Pandas, this is the group. You want to do something in the group. So for instance, in the group, I want to shift, but only for the group values, or I want to interpolate, but only in the group values, or I want to reverse, but only in the group values, right? So you can do this here in the aggregation context, but I will come up with something better even. Yes? Let me get to the... I'm almost there. I want to see the so okay, you can also do some filters in the aggregation context. I'm going to skip this one. Is this clear? Is the power clear? There's one thing I want to show, which I really like. Window functions. In SQL, these are called window functions. So that's the name. And in SQL, you do something like sum over group, partition by. In Polish, you say column foo, and then we do an aggregation expression, and we do this over the column we want to group. So let's say we do this here. But the cool thing about window functions is that we do an aggregation, a group by, but we do it in the select context. So we can select fruits, we can select cars, but we can also sum by fruits, right? So let's also show B. So we have the fruit apple, which is 3 and 2, and if we sum 3 and 2, we get 5. And that's what we see, sum by fruits, right? And banana is 5, 4, 1, which is 10, which we get. The cool thing is we can do a second window function over another group by column, over cars. And then we sum B by cars. And we can do any combination of groupers in a single select statement. But it can also be the case that you don't want to. So, okay, this is an aggregation function. It returns one value. What if I want to take, for instance, apple? I've got the group banana, and I want to reverse column B, but only within banana. So I want banana to be 1, 4, 5, and I want apple to be 2, 3 instead of 3, 2, right? Then I can also use these window functions, and I just say reverse over fruits. And then we flatten the result, because if we just reverse, we get the list, right? We don't want the list, we want it flattened. Flatten, sorry. Voila. And then we get this thing reversed. So this allows us to do very expressively, do stuff within groups, and combine those things, all in parallel, all super fast, and all very readable and expressive. Okay. I don't know about the time. Maybe we should wrap it up. There is some part about optimizations left, but how is it on the side of on the meat side? All gone. Yeah. Okay, there are okay, this is in 3 sentences. You can do it completely lazy, and then we optimize stuff for you. We do filters, we push them down, and actually what we do is we make sure that you do a lot less work than you needed to do if you just ran your query natively. That's the thing. And what I'm working to is a union of this expression type of polars and the lazy type of polars, and that you can just write .lazy.collect at the end. And what you did in eager will work in lazy, right?
I think yesterday was
no, yeah, and well, in lazy it's even more. So, for instance, if you do a filter behind the join operation, a join operation is really expensive. So it would be wasteful to first join and then do the filter. So we push this down. We do the filter first, that kind of stuff. But yeah, let's wrap it up. I think other questions.
Okay, we help you.
Use it and come with ideas. Something you miss, probably you miss some functions. I just want to prioritize my work on
the embedded in the